Okay, so there's a different type of problem in section 2.1 that we didn't have time to cover in class. So I just wanted to make sure we go through this in case it shows up on a test. Let me start with this. It involves a new idea, something called a geometric series. Even though we've been talking about sequences, if we start to add numbers together, we refer to that as a series. And what's meant as a geometric series is this particular sum of numbers, 1 plus 1/3 plus 1/3 squared plus 1/3 to the third, is developed from, like, how do I get from one term to the next is we're just multiplying by 1/3, right? Multiply by 1/3. In the world of geometric series, we often call that the R value. 1/3 squared multiplied by 1/3 again, you get 1/3 cubed, 1/3 to the fourth, and so forth. And sometimes we want to find the sum of a geometric series. So let's say I wanted to find the sum of these 5 terms right here. I could write that as 1/9, 1/27, 1/81. I could do a common denominator. But one way to do it, there's a kind of a clever way to find the sum. Let's say I wanted to find this. Let's write sum is 1 plus 1/3 plus yeah, I'll still write this as 1/3 squared, 1/3 cubed, plus 1/3 to the fourth. I want to find this sum. And the trick is if I take this sum and multiply both sides by the R value. So if I multiply both sides by this, the left side would be 1/3 of S. And if I multiply this by 1/3, 1/3 times 1 is going to be 1/3, and I'm going to put it right here. If I multiply this one by 1/3, it's 1/3 squared. That'll be right here. This one will become 1/3 cubed, 1/3 to the fourth. And if I multiply this one by 1/3, I end up with 1/3 to the fifth. And then the idea is if you take these two equations and subtract them, one, you could imagine a 1 there. 1 minus 1/3 S is 2/3 times my sum. But notice what happens. If I'm subtracting this whole equation from this one, 1 minus 0 is 1, but all of these are going to cancel. 1/3 minus 1/3, this minus this, cancel, 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 except this one. I have nothing minus 1/3 to the fifth. So it'd be negative 1/3 to the fifth. And S was what I was looking for, right? S is the sum of those numbers. So if I divide by 2/3, which of course is the same as multiplying by 3/2, this would give me the actual sum. You could work that out on a calculator. So anytime you see a geometric series and you want to find the sum, that's a clever way to do that. And that's going to come up in the problem I really wanted to show you here, which was, I think, this is a really nice problem. It's very relevant if you're going into the medical field and you're prescribing medicine to your patients. This is an idea you probably should be familiar with. So let's say this is number 35 from 2.1. A doctor is prescribing 100 milligrams of an antibiotic tablet to be taken every 8 hours. So when you take that pill, presumably the drug gets absorbed into your body. But over time, by the time you take your next dose, a lot of the drug is going to be eliminated from the body. So we're going to presume just before you take your next dose that 20% of whatever amount of drug was in the body is remained. So 80% of it has been eliminated from the body. And so the question is, how much drug, let's start with this, how much drug is in the body just after the third pill is taken? So here, let's just make a table and let's literally manually figure this out. So first dose, so I'm going to have doses here, and we're going to define Q sub n to be the amount of drug after the nth dose. So after one dose, and I know it's not immediately, but the whole full 100 milligrams of the drug is in your body. Not all of it's probably been dissipated to the bloodstream, but that's how much drug is in the body. After 2 doses, we get our new dose of 100, but then according to this, it says 20% of that. So this is what I would refer to as Q1, right? That's how much was at the beginning. And we're going to have 20% of what was in the body before. So this would be 100 plus 20% of 100. And if you work that out, that's pretty easy. 20% of 100 is 20, added to 100, we're going to have 120 milligrams of drug in the body. After the third, and we'll label this is Q2, isn't it? This is the amount after 2 doses. So after 3 doses, again, we get our fresh dose of 100 milligrams, and we're going to have 20% of however much of the drug was in the body before, which is Q2. So you can, and well, we're going to get to this, but you can maybe see this is more naturally described as a recursive sequence, right? Because the amount of drug after the 3rd dose depends on how much was in there in the previous dose, right? And that's the idea of a recursion. But if we actually put in the numbers, plus 20% of Q2, Q2 we have as 120, but let's go back to how we got that answer, which was right here. So that was Q2. So if I put in 100 plus 0.2 times another 100 and distribute this, 100 plus, this is going to be 100 times 0.2. And then 0.2 times 0.2 times 100 is 100 times 0.2 squared. And this simple, if you do this on a calculator, you're going to end up with 124 milligrams. So that is the answer to part 3. And this would be Q3. But what you want to notice here is if you keep going, if you do your 4th dose and do it the same way and actually simplify it, perhaps you should try this, but notice there's sort of a pattern here, right? 100 times 0.2, 100 times 0.2 squared. If you do the same thing for your 4th dose, which would be 100 plus 0.2 times Q3, and simplify it, you are going to get 100 plus 100 times 0.2 plus 100 times 0.2 squared, and then 100 times 0.2 cubed. And you start to notice a pattern here. And what you also hopefully notice is that this is looking like a geometric series, right? To get from here to here, you're multiplying by 0.2. From here to here by 0.2. This is geometric. R equals 0.2. Now, the question says if Qn is the amount of drug in the body after the nth tablet, write a difference equation for Q sub n plus 1 in terms of Q sub n. I didn't mention this before. A difference equation is also known as a recursive sequence, a recursion for short, recursion. And that's something we have talked about. That's telling us how do we get to the next drug amount in the body based on the previous amount. Well, we've kind of seen, let's slide this back down. When n is 4, Q sub n, if I want to know how much after the 4th dose, it's going to be 100 plus 0.2 times however much was there in the 3rd. After the 3rd dose, move it up here. For the 3rd dose, it's 100 plus 0.2 times however much was in the previous dose, right? 0.2. So this pattern is going to always tell you how much you have, how much drug is in the body. It's going to be 100 plus 0.2 times the amount of drug that was in the body in the previous, after the previous dose. Now, what's the interesting question here, right? If this patient keeps taking this drug, we saw, let's review again. After 2 doses, remember we started with 100 milligram tablet. After 2 doses, there's 120 milligrams. After 3 doses, there's 124. After 4 doses, you would expect this to be higher. Is there a limiting sum to this? We kind of would want to know, if we don't want this to skyrocket, right? We don't want our patients, the amount of drug to get too high, right? If we're being careful. So we want to know if there's a limiting value. And in class, we've talked about if this is a recursive sequence and you want to find the limiting value, we find the fixed points. And if you recall, the fixed points is when you set both q sub n plus 1 and q sub n equal to each other. And I usually like to call that L. So just going to make a note here. Using the recursive formula, the limiting amount can easily be found by finding the fixed points. So if I set L equal to 100 plus 0.2 L, subtract this over. So 1L minus 0.2 L is 0.8 L. So L would be 100 divided by 0.8. Doing some mental math, 0.8 is 4/5. And if I was dividing by 4/5, that would be the same as multiplying by 5/4. 4 goes into 125 times. 25 times 5 is 125 milligrams. And if you recall from what we said in class, when you find fixed points, this is only a candidate for what the convergence is, what the limit is. And if you recall, what we did is we had to have some numerical data to back that up, that this sequence really will converge to this amount. Well, we did collect data, right? We started with 100, we got to 120, 124. So it certainly seems reasonable that this is going to be the limiting amount of drug in the body after infinite amount of doses. However, the challenge on this problem is they want us to find a formula, there we go, for the amount of drug in the body in terms of N. The formula we found here is not a formula in terms of N, it's a formula for the amount in the next dose based on the previous dose, right? That's not in terms of how many doses. So using what our table, what we had before, let me just write summarize here. We had for Q3, we had 100 plus 100 times 0.2. I'm just going to put 0.2 now, plus 100 times 0.2 squared. For Q4, we had 100 plus 100 times 0.2, 100 times 0.2 squared, plus 100 times 0.2 cubed. So using that pattern, it's a geometric series. How much would I have after the nth dose? Well, I'd have 100 plus 100 times 0.2 plus 100 times 0.2 squared, dot, dot, dot. And the question is, what would be my last term in terms of n? Well, we can see that after the third dose, my biggest power of 0.2 is 2. After my fourth dose, it's 3. So it makes sense after my nth dose, this should be to the n minus 1 power. So this is a formula for q sub n in terms of n, but we'd like to simplify this. This is a series. Notice I skipped a bunch of terms, right? I just went to n. And it's a geometric series. And the start of this video, we talked about how to find the sum of a geometric series. I think it's easier if we factor out the 100. So we just have 1 plus 0.2 plus 0.2 squared, dot, 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 until we get to 0.2 to the n minus 1. Now, there is a formula. You probably saw it in class. You see it in the book for how to add a geometric series, but I caution against using it. It's not written, it's written slightly different. It's written as if you were adding up to just 0.2 to the n, and we're going 0.2 to the n minus 1. There is a way to use the formula cleverly and think about it. But what I would suggest is just find this sum the same way we did at the beginning. So if I want to find the sum of 1 plus 0.2 plus 0.2 squared plus dot, 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 0.2 to the n minus 1, remember the trick was I want to multiply both sides of my equation by the r value, which is 0.2. So I'm going to have 0.2s. I multiply this by 0.2, you get 0.2. This one by 0.2, you get 0.2 squared. Okay, now fill in the blanks, right? This would be 0.2 cubed, but there would be a 0.2 cubed there, right? And notice this one times 0.2 is going to increase the power by 1, so it would actually be 0.2 to the n. And the term before here that I didn't write, 0.2 to the n minus 2, if I multiplied that by 0.2, that would have been 0.2 to the n minus 1, right? And then we subtract, and we end up with 1s minus 0.2s is 0.8s. Subtracting 1 minus 0 is 1. All of these subtract out, except for nothing minus 0.2 to the n. So minus 0.2 to the n. And if I divide by 0.8, my sum is 1 minus 0.2, put parentheses to emphasize that, to the n divided by 0.8. That's what they were looking for. Now, what could I do with this? We already know the answer to this, but there's another way to show what's the quantity that remains in the body in the long run. In other words, as n goes to infinity. That's what we would have called the fixed point in the recursive sequence. And we already found that answer was 125. But you could also take the limit of the formula, right? If we just want to know, this is the sum after n doses, the amount of drug after n doses, we want to know what happens when n goes to infinity. So we're going to take the limit of that. And when you take, the only place to plug in infinity is right here. So we're going to have 1 minus 0.2 to the infinite power over 0.8. And what you have to realize is 0.2 to the infinite power is 0.2 times 0.2 times 0.2 forever. And because 0.2 is a decimal that is less than 1, if you keep multiplying it together, it's going to get smaller and smaller and smaller. So eventually it would approach 0. This term is going to go to 0, leaving me with 1 divided by 0.8, which is 1 over 4/5 is 5/4. But now remember, go back to, I probably need to adjust this actually. I just realized this. Let me go back up here. Remember how I used the trick here to find the sum of this? Well, the actual amount was this times 100. So let's actually just, let's multiply this by 100, which means we should multiply this by 100. I'll put it over here this time. So it should have been 5/4 times 100. Should be 100 there too. And we already did that. That's 125 milligrams, which we, again, had already kind of suspected that would be the limiting amount when we did the recursion and found the fixed points. So I just wanted to show you that because there is that weird part with the geometric series that you should know. Yeah, and hopefully this makes sense. Let me know if you have any questions.